Sir, good evening, sir. Professor Nagesh Kumar, sir. Sir, Professor Nagesh Kumar, sir. Hello. Hello, Professor Nagesh Kumar, sir.
Yeah, can you hear me now?
Yes, sir. Yes, sir.
Yeah.
So I have made a co-host, sir.
Yeah, that's right. That's why I could not talk to you earlier.
Yes, yes,
No,
yes.
it's fine. Okay. So let me also share the screen. Can you see my screen?
Yes, sir. Yes, sir.
Okay.
So later you can, in the more section, disable part annotation, sir.
Yeah.
And later you can take the spotlight, sir. In the annotations, you can click spotlight.
Yeah, I have done that.
Okay, okay. So at 6 o'clock I will start, sir.
Yeah.
So one of my colleagues introduced you, sir. So after that,
Okay.
around 6:05, so the lecture will start, sir.
Yeah, that's fine with me.
Okay, thank you, sir.
Shall I mute my audio right now?
Okay, sir.
Okay, thank you.
లీలా కృష్ణ
సార్ గుడ్ ఈవినింగ్ సార్.
అదే వినిపిస్తుంది.
ఓకే సార్.
అదే మిమ్మల్ని కో-హోస్ట్ చేశాను. ఐ హావ్ డన్ ఏ కో-హోస్ట్. సో
ఓకే.
ఓకే. So you can do unmute and you can introduce the speaker when I mentioned. Okay? Leela Krishna.
Okay, sir.
You have to unmute at the time
Okay.
of introducing.
Okay, sir.
Okay, okay.
Ramara, sir. Hello. Dr. Ramara, sir.
Please tell me.
Shall I continue, sir?
Now you can, not now. So I
Okay.
have 6 o'clock I will start.
Okay.
So, at that time I am going to intimate you. Now
Okay.
I'm
Okay. Okay.
just,
Okay.
so the speaker is checking his slides. Just.
Okay.
Good evening to all of you. Myself M. Ramarao, Secretary IGS Guntur Chapter. This is 22nd webinar of IGS Guntur Chapter. IGS Guntur Chapter established in 2003, organized a number of seminars, workshops, significant being IGC 2009 National Conference. I am thankful to Dr. D. Nagesh Kumar, Professor, Department of Civil Engineering, Indian Institute of Science, Bangalore, for readily accepted to deliver this lecture. Remote sensing, GIS and DEM for water resources assessment. Few announcements to participants before introducing the speaker. I request all the participants to stop video. And now we are going to chat with the host only. And during the lecture, if you have any problems related to audio and video, chat with me. Please do not share your information. And the questions also at the end of the lecture, but not during the lecture. After completion of the lecture, I will share Google Form link. And its purpose is your feedback and also sharing the content of this lecture in PDF. Question answer session through chat at the end of the lecture. Our next webinar tomorrow by same speaker, Dr. Nagesh Kumar, and the title is Climate Change and its Impact on Water Resources Assessment at same time, that is 6 p.m. Now I request my colleague, Mr. Leela Krishna, Assistant Professor, Department of Civil Engineering, RVR and JC College of Engineering, requested to introduce speaker. Leela Krishna, please unmute yourself and introduce the speaker.
Thank you, sir.
Yes.
A very cool good evening to all of you. It is a great privilege to me to introduce Professor Nagesh Kumar Garu on behalf of IGS Guntur chapter. Nagesh Kumar Garu received his PhD degree from the Department of Civil Engineering, Indian Institute of Science, Bangalore in the year 1992. He has been a professor with the Department of Civil Engineering, IISc, since May 2002. Earlier, he was with the IIT Kharagpur during 1994 to 2002 and National Remote Sensing Center Hyderabad during 1992 to 94. He was a Boycast Fellow with the Utah Water Research Laboratory, Utah State University, United States of America in the year 1999 and visiting professor in EMSE, Saint-Étienne, France in 2012. His research interests include climate hydrology, climate change, water resource systems, artificial neural network, evolutionary algorithms, fuzzy logic, multi-criteria decision making, and remote sensing and GIS applications in water resource engineering. He has supervised 9 postdoctorates, 1 is in progress, and 20 PhDs, 5 in progress. He is the co-author of 6 textbooks and published more than 200 papers in peer-reviewed journals. More details will be available in civil.iisc.ac.in. Now, I request Professor Nagesh Kumar Garu to continue the lecture. Thank you, sir.
Thank you, Leela Krishna, and thank you, Dr. Ramarao, for organizing this talk. I'm really feel privileged to give this talk in IGS Guntur section. I have a lot of attachment to Guntur district. I lived there for about 9 years in Macharla. So I'm very happy to be giving this talk for IGS Guntur section. And I sincerely appreciate the efforts put in by IGS Guntur section in organizing good number of webinars on varied topics. And I'm also aware of the other activities that IGS Guntur section is doing through my colleague, Professor Babu and others. So I'm really happy the way IGS Guntur section is working. Now, what I will do is I will try to talk about 3 important tools which are called remote sensing, GIS, and DEM, and try to tell you how they perform and what is the use and how we can try to utilize these tools for water resource assessment. So it will be for about 15 minutes duration, and then we can discuss briefly if you have any questions and other points. Now, before I start my presentation, I have to acknowledge my former PhD student, Dr. Anandi. She a portion of her work that here is done by her for her PhD. And she is right now working as an assistant professor in Florida A&M University, America. And for her, we had one more supervisor, Professor V.V. Srinivas. So I wish to acknowledge both of them for my presentation, or before I begin my presentation. Now, what we will do is we will briefly introduce these three tools: remote sensing, mainly for land use, land cover estimation; GIS for watershed delineation as well as map stacking; and DEM for drainage pattern estimation, especially using one particular source of DEM database called SRTM data. Once we familiar with these three tools, I try to utilize through a hydrologic model called AV-SWAT model and try to utilize it to estimate water resources with all these three tools put together.
Sir, excuse me, sir, Professor, sir.
Yeah.
So
Yeah.
use the pointer, please.
Yeah.
Okay.
Sure, I'll do that. Okay. So let me start with the first tool, remote sensing. Actually, what we're doing right now is called remote sensing. I'm sitting here in some corner of India, and you are trying to see me from different other locations all over the country. And that's basically you're trying to sense me through the spectrum that is transferring the signal to you, to your monitor or to your computer screen. And from there, you're able to visualize me. So what basically we talk about remote sensing is trying to study something about an object without physically coming in contact with it is called remote sensing. So like your TV control, TV remote control, or any such things. So the major advantage is that, if you are trying to do this over a long distance and try to get some information, then we get a very good synoptic view. Just to give you an idea, what you are right now is entire India and its surroundings in one satellite image. I think, of course,
Excuse me, sir, your audio is intermittent.
To show the entire India and its surroundings.
Sir, excuse me, sir, your audio, so it is intermittent. Okay. That is a cut is there. Please.
How about now?
So a little problem is there. Intermittent. That voice is not. Now we can.
I see. I don't know. My internet connection should be all right. But can you hear me now?
Yes, sir. Yes, sir.
Okay. I'll try to make it slightly louder. Hopefully, it will be visible. But anytime, if it is not audible, please interrupt me.
Okay. Okay. Sir.
Yeah. So as I said, this is the thing offers us one important aspect, that is synoptic coverage of a large area in one image. So what we're seeing is, India and its surroundings in just one image. And what you're seeing in the media, the red color, please train your eyes for the next 1 hour. When you see this red color, it actually talks about healthy vegetation. Okay, although you're seeing in red color here. I'll explain why we are doing that. One major aspect that we try to measure through remote sensing is electromagnetic radiation. So we have, from any source of light, we have an electric wave, and we also have a magnetic wave, which are orthogonal to each other. Both are perpendicular to the source of energy. That source of energy can be anything like sun, or torchlight, or flashlight, or any such thing. From any light, we get the EMR spectrum. So when we get this electromagnetic wave, we try to measure it either in terms of the
Again, audio problem, sir. So do you have the earphones, sir?
In terms of frequency, that is how many number of peak possible. Sorry, yeah, I'm using earphones. I don't know what could be the problem. Well, it's very important that we should resolve that problem before I get into my remote sensing.
Intermittent voice break is there, sir.
Mhm. Can you just give me 1 minute?
Okay, sir.
I'm wondering whether it is due to internet connection.
Okay.
But can you hear me now?
Yes, sir.
Okay.
Sir, kindly switch off your video, sir. Then the internet resources may be
Yeah.
diverted to audio.
Okay, fine. I will do that. I'm switching off my video right now. Okay. And still, please don't hesitate to interrupt me whenever audio goes down. Can you hear me?
Yes, sir.
Okay. Yeah. Sorry for the interruption. So, what we are trying to look at is this so
I think it is internet problem, sir.
when
So it is a break in the voice.
like this,
Just wait, sir.
what we
Wait
are
1 minute, sir.
looking
It is a break in the voice.
at is the
So, hello.
Can you hear me?
Yes, sir.
Okay, so I should start this screen
Okay,
sharing
sir.
again. Can you see the screen now?
Yes, sir. Yes, sir.
Again, whenever there is audio break, please stop me.
Okay.
I see that there are some people who are using video. I hope that will not be a problem. Yeah.
I request all the participants to stop video. Okay, sir.
Okay, so I'll continue. So when we try to get this electromagnetic wave, it's available to different wavelengths. And I just try to show you what is the kind of range of wavelengths that are available to us to play around and try to do the remote sensing. And that's a very wide range. So you can see here on a logarithmic scale, the wavelength is shown in different micrometers, starting from 10 power minus 8 micrometers to about 10 power 9 micrometers. In this entire EMR spectrum, what we can see as a human is only a very narrow region, which is called a visible region. That is about 0.4 to 0.7 micrometers. I keep referring to these wavelengths, so I request you to note this point. So 0.4 to 0.7 micrometers is the only wavelength region of the EMR spectrum that is sensitive to human eye. Whereas we have sensors which can see X-rays, we can see ultraviolet rays, we can see thermal infrared, etc. So when we acquire images or information in these wavelengths which are not visible to us, what we do is we give some false color to that. And by giving that false color, we try to see what is that we cannot see in those wavelengths. So that's why we try to create some kind of what are known as false color composites. So when we do that, the kind of image that I have shown you just 2 slides before is a false color composite. So here, what you are seeing in red color is actually healthy vegetation, and that's given red color because it is very bright in infrared wavelength. So that's one aspect, very important aspect of EMR spectrum. And in that, we are trying to use different wavelengths to do the remote sensing. And today, I'll be focusing mainly on visible region and slightly beyond that up to infrared, thermal infrared region. So this is a portion that I'll be focusing on. Although we have good number of satellites and sensors operating not only in this range, but also in microwave range. So let me now focus on this portion as far as remote sensing is concerned. Then another important aspect is that when we try to get the remote sensing image, it's better to understand the characteristics of a remote sensing system information through spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. I try to illustrate each one of them briefly now, but what I will do is to save some time, I will be focusing only on spatial resolution and temporal resolution in today's presentation. So when we talk about spatial resolution, what we mean is the smallest elemental area over which we make an independent observation from any sensing platform. So if I now call this area or a square box as, let us say, 20 meters, means 20 meter by 20 meter square box area is just one pixel or one dot in the satellite image or in any image that is acquired through that system. So, now when I say that a satellite has a spatial resolution of 20 meters, what it means is that one 20 meter by 20 meter on ground will be just one dot on the image, or one pixel on the image. So if we have a satellite image which talks about very coarse spatial resolution, means let's say it's represent 250 meters by 250 meters as just one dot or one pixel, then we are talking about covering large area at a coarse spatial resolution. So what you can see here, just to illustrate the point, is an area that is covered, which is about roughly 200 kilometers by 200 kilometers. The entire area is covered in one image. Okay, and the spatial resolution of the satellite here is very coarse, but it is covering large area. As a matter of fact, entire Ganga basin and the surroundings are shown in this image. Instead, if we just try to look at only this yellow color box that is there inside it, that itself is one satellite image like this from another satellite. Okay, and this is from a satellite called MODIS sensor, and whereas if you look at this satellite, this is from a Landsat ETM Plus satellite. Okay, so here what happened, this small box, which is roughly about a small portion of it, okay, and that itself is one image here. And then if you try to look at the small yellow box within this, okay, and that yellow box itself is one image here, and that is from another satellite called Greece satellite Iconos, okay, and that has a very fine spatial resolution. And if you further look at this small yellow box, that itself is one satellite image here at much finer spatial resolution. So when we are trying to acquire satellite images, we can acquire image at a given spatial resolution. So if you are interested in studying a large basin like Ganga, then this spatial resolution is good enough. Whereas if you are interested in studying, let's say, just Guntur and its surroundings, then we may want to have a very fine spatial resolution at this kind of satellite data. So depending on our need, we can try to go for a particular spatial resolution. Why I'm mentioning that is, a satellite image, if it costs, let's say, 25,000 rupees, this entire thing is 25,000 rupees image. Whereas if you're trying to look at this spatial resolution, roughly we require about 16 images to cover this entire area. So 16 and 25,000 rupees you have to spend. And if you want at this spatial resolution for this entire Ganga basin, you may be looking for about 500 to 600 satellite images to prepare the image for this entire area. So depending on the funds available, depending on the need of our interest, we can try to acquire images of our required spatial resolution. That's a very important component as far as satellite remote sensing is concerned. Now, other important point is the temporal resolution. By definition, satellites rotate around the Earth at regular intervals of time. And if that interval is much finer when compared to 24 hours, then what happens is it will be covering different segments of the globe during each of its coverage. So depending on how much it is covering or how much it is rotating, at what speed it is rotating, you can cover the entire globe over a few days. For example, if a satellite takes about 22 days to cover the entire globe, that means if you have acquired image for Guntur today from that satellite, after 22 days, we can again acquire the image for Guntur from the same satellite. So that means you know how this image or Guntur city is looking today and how it is looking 22 days after, or again 22 days after, and so on and so forth. And that kind of images that are acquired at regular intervals of time for a given location will help us to change or monitor change in land use, land cover, temporal variation, and monitoring of dynamic events like cyclone, flood, volcano, earthquake, etc. Like we acquire an image before a flood event and we acquire an image after the flood event, and we compare them to see what is the change that has taken place. And just to drive that point home, what I'm showing here is the entire Krishna River basin, which comprises of states like Maharashtra, Karnataka, Telangana, Andhra Pradesh, etc. So all these states, all the entire Krishna basin is shown here. And this is in January 2001. And 2 months later in March, May, July, September, November, all in the same year, but bi-monthly satellite products. So you can see a change in the land use, land cover by looking at different colors. So if you recall, I mentioned to you that what you see in red color is healthy vegetation. So that being the case, we can see that this entire area, there's hardly any red color here in January. But by the time we come to September, we can see that there's considerable amount of red color. And that's because of the monsoon period where we have gone for considerable amount of agricultural activity. So entire area is now agricultural area. But even in summer, you can see there is some red portion here, and that is actually Western Ghats forest region. Just to give you an idea, this is the place where we have Vijayawada. Okay, so now you can see this temporal variations that are taking place in a given region by acquiring satellite images through the temporal resolution aspect of it. So these two important characteristics, that is spatial resolution and temporal resolution, will help us understand better and utilize that resource for land use, land cover estimation and other changes. I'll be briefly touching upon this topic again, but let me move on to the next tool that I want to introduce to you, that is called Geographic Information System. The name sounds big, but there's nothing big in it. It's like, all of you are used to using Microsoft Excel. In Microsoft Excel, if I have students' marks and their names in 2 columns, if I want to sort them, then what I will do is I will sort only, let us say, the marks column, then the marks of one student will go to other student. But we don't want that. What we should do is we should sort it in such a way that both the 2 columns are sorted together, so that highest mark fellow will be at the top. And that's what you try to do by arranging them in ascending order or in descending order. That's if you have one sheet. But let us say that for the same class of students, you have in another Excel sheet the marks in another subject, and in another Excel sheet you have marks in another subject. But what is common among all these Excel sheets is the names of the students are one column which is containing the name of the students or names of the students. So with respect to that column, we can try to now find out what are the total marks obtained by each student and then try to arrange them in ascending order or descending order to find out who is the highest mark fellow and all those things. So when we are doing that, the first portion that I mentioned is typically referred as DBMS, whereas the second one where you have the data in different Excel files and try to put them together, it is called as RDBMS, or Relational Database Management System. And if that the attribute that I am mentioning is the name of the student is not name of the student, but name of the location. For example, one college or another college and so on and so forth. So in that case, that attribute is now spatial location information is also there. So then we are talking about spatial database management system, which is simply called as Geographic Information System. The main advantage of GIS is that we can try to represent any feature. I mean, that's why it is also called as feature model. You try to represent any feature on our surface, either by point, line, or polygon. So what you can see here is that let's say this place we have Survey of India benchmark or something like that. That benchmark will become then a point information. And if you have a river or canal or a road network, that means basically it's all line. You know, I'm saying line, but you are seeing a curve here. These are all segments of small straight lines which are joined together to form this kind of curve. So this is a line. So you can try to represent different linear features using line aspect of the feature. The other one is polygon or an area. So here what happens is, you try to show a closed polygon. The only difference between line and a polygon is that line starts somewhere and ends somewhere, whereas polygon ends at the same place where it started, therefore it closes. Okay, so you can try to represent various places like water body, political boundary of state, or political boundary of Guntur district, or something like that. So those things can be shown as polygon. Now I'll try to show you some example here. The first, these are all about 5 maps that you can see here. All these 5 maps belong to the same area. Okay. Now the first map is showing the land use. Means let us say that this portion is agricultural area, and this portion is residential area, and this is a water body, and this is a park. So there are 4 different land uses that are there in this area. Each one of them are shown as different polygons. So land uses can be shown as a polygon. In the same way, if you talk about soil type, Guntur district is very popular for black cotton soil. So if you have black cotton soil somewhere, and you have a red laterite soil somewhere, and laterite soil or a clayey soil somewhere else. So if you have different types of soil types, that map can be again shown as a polygon feature. And let's say now there's a stream, this blue dotted line, and on that we have some yellow dots. Those are the places we are trying to measure the stream flow. Okay, so these points are now stream gauge locations, and that is shown as point information. Stream itself is shown as a line feature, and watersheds or watershed boundaries are again shown as polygons. So you give me any feature on a surface, we can try to show it as a line, point, or polygon. And the main advantage is that with GIS, we can try to overlay all these things. The only common attribute, like the way I mentioned in the case of name of the student, here the common attribute is the spatial location. That spatial location can be XY coordinates or latitude and longitude. So if you specify that, then all these maps talk to each other. For example, by looking at all these maps together through GIS, I can answer a question like how many stream gauges are there in black cotton soil region. So I overlay this map and this map to identify the stream gauges which are located within black cotton soil polygon. And that will try to answer that question. Like that, query-based analysis through multiple layers of stacks of maps is something that we can do with one common attribute, that is locational attribute. Just to drive that point home, how or where we can try to use GIS for water resource assessment. Let me just give you a glimpse of what all we can do with GIS for water resource assessment. So in the stage 1, in the first stage, for database creation itself, we can try to use GIS, that is collection, processing, inventorying of hydrologic, meteorologic, and hydrometeorologic or geological and auxiliary data. All that can be collated. It can be temporal as well as spatial. For example, if you have 10 recording rain gauges, all the recording rain gauge data can be collated into GIS database. And the data creation and relating them to specify the specific locations, spatial locations, etc. The other one is once we have this database created, then stage 2, we try to extract technical information. For example, if you have the rain gauges at multiple locations, and if you want to find out the representative rainfall of Guntur district by looking at the rain gauges available within Guntur district, then what we do, we try to do some kind of interpolation. One popular thing that you study in hydrology is the Thiessen polygon approach. So we can try to draw Thiessen polygons and try to get the represented rainfall for the entire Guntur district using GIS. In the same way, we can try to do many kinds of things like topographical modeling, network modeling, and map overlay, etc., which I have briefly mentioned already. And we can also extract geostatistics. That is the next stage. And third stage is knowledge dissemination. Once we interpolate and create this kind of database, then we can try to make this database available to different users for whatever the purpose they are trying to use it. For example, Google Maps. Google Maps will be used by a taxi driver or Uber driver, basically to commute from one point to another point using GIS. In the same way, if you give it to one hydrologist, he would like to use it to assess the water resources in a given location. And if you try to give it to a seismologist, you would like to identify the places where the earthquake or earthquake-prone zones are there within a given region. So, identification of, let's say, folds, faults, etc. All that can be done through knowledge dissemination through GIS. So GIS helps in database management, technical information extraction, and knowledge dissemination. In all these cases, GIS is extensively used. Now, the last tool that I want to introduce to you is DEM, or Digital Elevation Model. Again, the name sounds big, but there is nothing big in it. Just to give you an idea, if you are already familiar with, what you're seeing is a three-dimensional view of a topographic feature, and this red line that you are seeing here is actually called as ridge line. Basically, the point or the contour of highest elevated points around the region. So this is called ridge line, which is also can be called as watershed boundary, if you consider this entire thing as watershed. And you can also see a brown line that is called the valley line, or the point or the line joining the points of lowest elevation. So that's valley line. Okay. So these can be derived through digital elevation data. This is again nothing much. Like as I said, DEM is again a simple playing tool. What we can do is, you know already that you can get elevation data. Even if you are using dumpy level or total station, you can try to get elevation data. But when you get elevation data, you try to get that elevation data at a particular location by putting a staff base there. So you know, let's say the coordinates of that XY coordinates of that location. For that XY coordinates, now we are getting elevation. And that elevation data, along with XY coordinates, if you store it on a computer system, it becomes digital elevation data. And if you now play around with it, you talk about digital elevation modeling. Okay, so let's play around with it for some time. So what you're seeing here is, this is X coordinate and this is Y coordinate. And what you're seeing is Z coordinate here, where a Z coordinate, where you're trying to see the elevation for every XY coordinate. We're trying to show what is its corresponding elevation. So you can see that there's a high elevated point here, and there is a very high elevated point here, and there is a low elevated point here. Then what we can do is we can also try to join a smooth line through all these points and draw a curve like this. Then we can as well generate three-dimensional surface, and that is what you are seeing here. So you can now clearly visualize a peak here, you can see a peak here, and you can see a valley here. So that's basically simply the elevation data that we have done, obtained through, let's say, using our dumpy level or something, and then you are trying to fit a smooth curve through them, through a spline or whatever it is, and then you try to get these peaks and valleys within a given region. Now, what we can do with this digital elevation data as far as hydrology is concerned, it's an excellent resource for considerable amount of hydrologic analysis. So I will try to explain all that. If we have the digital elevation data available, then from that, we can try to talk about catchments, we can try to talk about watersheds, we can also talk about basins or basin identification, and all the streamlines that you are seeing here can all be derived through DEM. Okay, so what we start with is we try to estimate the flow direction, flow pathways, flow accumulation, stream network, catchment area, and also upstream contributing area, and slope and aspect information. All this can be derived through that simple elevation data that we have and through DEM. And please pay your attention for about 10 minutes. I'll try to make sure that you become experts in trying to do all these aspects. So let us start with a simple classroom example of, let us say, a 3x3 box. Means you divide a given region, small area where you have dumpy level, okay? Divide that into 3x3 box. Let us say each box is about, this is 10 meters, this is 10 meters, this is 10 meters, 30 meters by 30 meters is the total box size. Okay, so at the 10 meters by 10 meter box, at the center of that location, you put the staff gauge and get the elevation. Let us say that elevation is 67 meters or 67 with respect to some benchmark. Okay, and here the elevation is 56, and here the elevation is 49, and so on. So we record for this 30 meter by 30 meter box, that is 3 by 3 box, at the center of every box, we know the elevation. So these are the elevation values which are now stored in a computer system along with its XY coordinates. Now, this is our basis. With this, we can try to do lots of things. For example, one thing that you can notice here, this elevation is 67 and this elevation is 56. That means it is at a lower point when compared to this point, right? Now what we can do is we can find the elevation difference. But what we can also find is once we know the elevation difference, and if I also know the distance between these 2 points, which is 10 meters, so I can also estimate the slope. Okay, so if, for example, if it is just 1 unit, that is, let's not forget about 10 minutes, simply call 1 unit. Okay, so what we can do if you want to find the slope in this direction, 67 minus 53 by 1 unit. That gives me the slope in 14 or percentage wise also you can express that. So I try to estimate the slope in this direction. I also try to estimate the slope in this direction. And I can also try to estimate the slope in this direction. But for this direction, the distance is not 1 unit, but it is square root of 1 square plus 1 square, that is square root of 2. So 67 minus 44, 67 minus 44 by square root of 2 is the elevation slope in this direction. Now imagine if you are here. From this point, we can try to estimate the slope in all these directions. How many directions are there? 8 directions are there. In all these 8 directions, I try to estimate the slope. Some may be upward slopes and some may be downward slope. Among them, I try to estimate which is the steepest downward slope. And in all languages, we have a simple proverb saying that God only knows the truth and water only knows how to flow in the steepest slope direction. I hope that many of you are Telugu people, so I can say that Neeru Palla Merugu, Nijamu Devude, right? So that's a simple concept. So if you try to look at this, from this point, I try to identify the direction which they have the steepest slope, downward slope. Means from this point, water will try to flow in that direction if there is any water here. So what I do now, I try to replace this number 44 with an arrow in this direction because water would flow in this direction. I do that for every grid box. Okay, so I replace this 9 by 9 and 3 by 3 grid with 3 by 3 arrows now. There are 9 arrows in each arrow. For example, here the arrow is in this direction, here the arrow is in this direction, or maybe in this direction, and here the arrow may be in this direction, etc. That's a simple concept. So now what we are doing, for each pixel or for each grid box, we are trying to identify in which direction water would flow. Now that you know the concept, I will slightly make it larger. This is 3 by 3 box. Now I'll try to make it 5 by 5 box. So you can see here for 5 by 5 box, for every box, I am trying to show from that box in which direction water would flow. Right? So if we have this, that is the first aspect that I mentioned to you, flow direction. Then what I will do is I'll try to see that water is flowing from here. Where is it going? It is going here. And from here, where is it going? It is going here. So now I try to connect all these arrows. Okay. So if I try to connect all these arrows, now what happens? I am trying to talk about flow path. So flow goes from here it goes here, from here it goes here, and from here it goes here. Okay. And like this, we have now complete flow path map. For every grid box, we are trying to show how the flow will take place. And as you can notice, all the grid boxes are finally draining into this location, which you can now call as mouth of the river basin if this itself is a river basin. Okay, and if you call that as a river basin, maybe this is a main river, this is a tributary, this is another tributary, and this is another tributary. Okay. So what we did, we simply use elevation data and try to get the flow path map and also flow direction map. Then what we can do, we can also see that at this box, I am getting water from 3 different grid boxes. And if you look at this, there are about 11 grid boxes which are contributing to this location. And if you look at this, this is 5 by 5, all 25 grid boxes are contributing to this. Okay. That also talks about what could be the amount of flow that may be taking place. Here only 3 contributing, and here 11, here 24. So you can also talk about what could be the stream width or depth or the flow depending on how many number of cells are contributing. So we can also get the flow grid and contributing upstream cells for every location, for every grid point. So that's what we can try to do. So in a nutshell, the algorithm that I explained to you is popularly known as the D8 algorithm because we have 8 directions, and based on that, we are trying to talk about flow path, flow network, etc. So in summary, we have the elevation data, and using that elevation data, we are trying to get the flow direction and using that flow path. And then what I am showing here is that this is getting, for example, this there is no contributor from upstream, and here 1 cell is contributing, and here 3 cells are contributing, here 8 cells are contributing, and so on and so forth. So the numbers that are shown here are how many upstream cells are contributing to this given location. And entire thing is driving into this location. Now, you can also say, if I put a threshold, saying that show me only those grid boxes which are having at least 2 cells contributing from upstream. So those are shown in blue color highlighted here. So these are the places where we have large number of cells contributing, at least 2 cells contributing into that location. Now, based on that, we can try to call this as a mainstream and others as substreams or tributaries or whatever the way you want to call it. And based on that, what I can also say is that for this, these are the cells that are contributing. For this, these are the cells that are contributing. Therefore, for each one of them, I try to give different colors. Okay, this is one color, this is one color. That means if this is one watershed, I am trying to identify within that this is one sub-watershed, this is one sub-watershed, this is another sub-watershed, this is another sub-watershed, and so on and so forth. All that is from this simple elevation data. So through DEM, we can do a lot of hydrologic analysis for all the purposes that are required for hydrologic analysis. Based on that, we can talk about order of the stream, and we can talk about the stream length, stream strength, and many other aspects. Slope aspect, all those things can be derived through this DEM approach. Now, the only question that we have to ask then is, where is this elevation data available? One possibility is that take the dumpy level, go around the whole area and try to get the elevation data. But other way around, we can also use remote sensing to get the elevation data. So what you are seeing here is one such source. This is through remote sensing, but it is not through satellite remote sensing. This is through Space Shuttle Endeavour. Through this, the digital elevation data is obtained for the entire globe at a very fine spatial resolution. For example, for our country, this data is available approximately for every 80 meter by 80 meter grid box. The elevation data is freely available. So in the Google, if you type SRTM DEM, you can freely download the DEM data from this source. This is not the only source, but this is one very good source for digital elevation data. Means if you now go download this data for a given region, we have data for every 80 meter by 80 meter grid box, what is the corresponding elevation. I will be skipping the technique that is used to estimate the elevation using this satellite, this space shuttle, which is referred to as radar interferometry. Using the technique, they try to get the elevation data for every location over the entire globe. And the spatial resolution depends on the latitude. And for our country, it is at 80 meter spatial resolution. So this is the data that I am trying to use for the next illustration. So I try to first of all show you that SRTM data for a portion of Krishna River Basin, that is Karnataka portion of Krishna River Basin. These are some divisions that I try to make it lower Bhima, upper Bhima, etc. So you can try to see for this region, if you try to download the DEM data from SRTM, the DEM data looks like this. It looks like a very innocent grayscale image, okay? But trust me that every pixel here is trying to show you what is the elevation at that location of 80 meter by 80 meter box in terms of, with respect to, let's say, mean sea level. Okay. So, this is just not one image like the way you are seeing here. The SRTM data is available for this portion as one image, and for this portion as one image, and for this portion as one image, and so on. So all these images, which are also referred as tiles in SRTM nomenclature. So all these tiles are put together to prepare a DEM database for a given region using GIS. So once we create this kind of DEM database, we can do it. I mean, this is only for Karnataka portion of Krishna Basin, but what I will do is I will extend it and try to show it for the entire Krishna River Basin. Sorry, Telangana should have been there, but this is an older map. Okay, so if you now see this map, please remember this map shape in your mind. Then for this map, using the DEM data, SRTM data, and that simple D8 algorithm that I have explained to you, we have derived the drainage pattern for the entire basin. And that's what you can see in this picture. I refer to this picture in my classroom as African hairstyle because it is so dense that you don't see any drainage pattern here, but only black color and slightly white portions here. But just to show you the direction, the drainage pattern, I will now take this small rectangular box and zoom it. Okay, now we can try to see some drainage pattern. And I further take a small rectangular box here, okay, and zoom it. And you can see a clear detailed drainage pattern. You remember when I showed you a drainage pattern, actually, they are all straight lines, okay? But you are seeing them as curves here because they are all segments of small straight lines added together for every grid box to get this kind of curved lines or features. So that's the way we can try to derive the drainage pattern or the detailed drainage pattern for a given basin. Now it is so simple that I give this as an assignment in my classroom to my students. So that take any river basin of your interest, download SRTM DEM data, and derive the drainage pattern for that basin. You can also identify subwatersheds in the same concept that I have explained to you for a classroom problem of about 5x5 grid box. And that was a 5x5 grid box for you. And what you are seeing here for Krishna Basin is approximately about 2000 by 2000 grid boxes. So that's basically the summary of those three tools: remote sensing, GIS, and DEM. As you can just make out, remote sensing can be used to derive a lot of land-use land cover information and changes that are taking place in time. GIS for map overlay technique and extracting information, and DEM for drainage pattern and other aspects, topographic features. And finally, we require a good hydrologic model, which will try to include the inputs that are coming from all these features, all these tools, and try to assess what is the water resources of a given basin. The hydrologic model that I'm going to talk to you is one such model called AV-SWAT. SWAT stands for Soil and Water Assessment Tool, and when that SWAT is floated on a GIS platform called ArcView, it is called AV-SWAT model. And AV-SWAT model has many interesting features. It's basically physically based distributed hydrologic model, and it can do rainfall runoff modeling on a continuous time basis, but will also provide considerable other information like sediment yield, agricultural chemical yields, and pollutant transport, many other features, groundwater component, evapotranspiration component. All those things can also be estimated through this AV-SWAT model. I'm not advocating for this model. There are many other models, but this SWAT model, like some other models like HECRAS, etc., are freely available. So you can Google for AV-SWAT or especially for SWAT and download the data, download the software. And if you are more interested, you can also download the source code, which is written in Fortran, and play around with the language to modify the model parameters if you wish. So let us try to use this model. And when that SWAT model, if it is floated on RP platform, then it is still the heart of that. But AV or RPU GIS platform, what it will do is try to provide a very nice front end as well as a nice back end. So front end, we'll try to talk about interaction with other features like from DEM database if you have something, from remote sensing database if you have something, from IMD data if you have some Excel sheets. We can try to put them together for rainfall, for temperature, wind speed, etc. So all these data are collated and provided to this SWAT model. And SWAT model itself would like to divide this entire basin into the drainage pattern and also subwatersheds, which we can do it through our D8 algorithm that I have just explained. So we can try to divide, and those subwatersheds in SWAT model are referred to subwatersheds, if you want to call, as hydrologic response units or HRUs. So that's what is done through SWAT model. And to try to play around with this model, we can try to do what is known as calibration and validation. So provide all this information required for a given basin and then run the SWAT model so that you know what is the water source available from that river basin. So just to drive that point home or to illustrate that aspect, I will now take one small portion of Krishna River Basin, which is in Karnataka, called Malaprabha River Basin. After Malaprabha goes to Bhadra, Tungabhadra, and then joins Krishna. Okay. So this is the basin, which looks like a very small portion Karnataka map, but that itself is about approximately 2,564 square kilometers. Okay. And on this, what are the basin that you are seeing here? What are the pink dots that you are seeing, pink triangles that you are seeing here, are all the places where we have the rain gauges. So we talk about Thiessen polygons, etc. And we also have one pink dot or pink circle. That's a place where we have meteorological station where we measure humidity, temperature, wind speed, etc. So that's the data that is used to model the hydrology of this basin. Now, for the land use, land cover, that is, what is the type of land, agricultural land, built-up land, forest land, grassland, etc. This information is derived through remote sensing. In case if you are familiar with remote sensing terminology, this is actually done through Indian remote sensing satellite IRS list 3 data merged with panchromatic data to derive land use land cover information for the Malaprabha basin. And entire basin now you can see different land use land cover categories. In the same way, we also derive the soil map, and this soil map is again derived from remote sensing, but it is also compared with the soil map that is available from NBSS and LUP, that is National Bureau for Soil and Soil Survey and Land Use Planning, Nagpur. So from there also we obtained the map and compared to see this is the soil map. So we have the soil map and we have the land cover map. Now these two maps, then what we can do is we can also try to take the SRTM DEM data. So what you are seeing here is the digital elevation data available from SRTM. You don't see numbers, but you see different colors because for a given elevation range, I have given different colors. So you can see that the lowest elevation portion, 632 to 671 meters above mean sea level, is given this color. So this is basically the ridge line, and this is the valley line. Now, on this digital elevation data, we use our DH algorithm that I just explained to you and derive the drainage pattern. You can see the drainage pattern now. Now, in this drainage pattern, what I can do is, all this area, all the streams are coming and joining here, and all the streams are also coming and joining here. So I can say that whatever the water that falls in this portion will get finally poured into this location. So this is referred to as one pour point. And this could be one more pour point. This could be one more pour point. This could be one more pour point, and so on and so forth. So all these pour points finally will flow, water will flow through the system, and everything will reach this location. And this is the place where we have one dam called Malaprabha Dam. So what we are trying to do is we try to model the flow through this entire region and estimate the flow that is taking place, that is reaching here, compare that with what is actually observed here. And if those two compare well, that means the model is calibrated and it is ready for future use. So that is what is done through this. So you can call now this as one subwatershed, this as one subwatershed, and so forth. And these are the 4 points that I mentioned to you. Okay, 4 points, and these are the subwatersheds. You remember, all this is done through that simple concept of DH algorithm. And these are all GIS layers. So I can try to put as many layers as possible. So this is just watershed map. On that I can now put the drainage map, and I can also put my 4 points. So I can try to see how the water is flowing in this entire basin. Okay. So now I use simple concept based on SES curve number, etc., using SWAT model, and try to estimate the flows at this location and compare them with what is observed there and the calibration. And it means if they are not compared, if they don't compare well, we play around parameters until they compare well. And like what I said, if you write the subclass here, you can see the land cover details available here. In the same way, soil data is available here. Okay. What is done is, it's very simple. if I now let us say that, this is pasture, this is water body, this is urban area, forest, agricultural area, etc. So if I see that one grid box is agricultural area, I try to count how many number of grid boxes are there in agricultural area. Okay, let us say 200 grid boxes are there in subbasin 1. And those 200 grid boxes, for each grid box, if I know the spatial resolution, let us say 100 meters. Okay, so 100 meters by 100 meters or 10,000 square meters is one grid box. So 200 such grid boxes. So 200 into 10,000 is your total square meters of agricultural area. In the same way for forest, in the same way for urban. And so for each subbasin, what is the total area under each type of land use? Same way, what is the type of soil cover? The soil, like clay, loam, skeletal clay, etc. And that information is also obtained. So once that is obtained, we try to use this information and SWAT model to provide the rainfall data to get the surface runoff. We also get water flow, groundwater flow, percolation, evapotranspiration, and other things from this model. Now, if you just focus only on the surface flow or the runoff that we are getting, or the stream flow that we are getting, then we compare that with the stream flow that is observed. And if those two compare reasonably well, with R square of about 0.95, which we can say that they are comparing well, the model is ready, calibrated well, and then it can be used for any future rainfall scenario. Give me the rainfall, I should be able to tell you what could be the stream flow or the inflow into the dam at that location. And this is done on a 10 daily time scale, but we can try to do it on a daily time scale or a monthly time scale or any other time scale. So the water resource of a given basin can be estimated using all these tools, using whatever I just explained. Okay, so that's what we can try to do as far as remote sensing, GIS, and DEM. There are excellent tools for modeling water resources. And once we know what is availability, we can also talk about planning and management. For example, if you're a dam, then we can try to see how much water should be released from the dam for a given period and for given purpose. Is it for hydropower, for irrigation, for drinking water? All that management is also done once we assess the water resources. What we require is proper image processing of remotely sensed data, DEM, and spatio-temporal analysis with GIS would be very effective for water resource assessment as well as management. Now, assuming that some of you might be interested in future research in this domain, I try to cover some aspects which are not covered so far. That is, we can try to use microwave remote sensing, which has major advantage of penetrating through the clouds. So even during monsoon period, we can get some very good images using microwave data. Whereas if you're using other satellite data, optical data, we will not get any information but clouds. Okay. Whereas we can also use hyperspectral data, which is extensively being used nowadays. As of now, from Indian remote sensing system, we don't have hyperspectral data, but for high-sis satellite. Otherwise, globally also, a good number of platforms are making this hyperspectral data available into the near future, and that offers excellent tool for much better land use, land cover discrimination. And synergy of multispectral, multi-day data is also a very useful tool for the future research. Image processing, and there are lots of challenges in DEM. I've shown you a very nice DA algorithm, but even when you use it, there are a lot of challenges, and they can be overcome with better algorithms that can be developed. And we can also use this to model impact of climate change on water sources, which I'll be briefly talking about it tomorrow. And DSS floated on decision support system floated on GIS, like the way you have Google Maps, etc., will also be very useful tool for floating GIS on a multi-user friendly platforms. So that's what I wanted to say as far as this lecture is concerned. And I am open to questions now.
Thank you, sir, Professor Nagesh Kumar. So now, before question answer session, I will share Google Form link. I request you, all the participants, to copy this.
I hope there are no more interruptions, right? Audio was okay?
No, audio is clear, sir.
Okay. Now I have to go to chat box, right?
Yes, sir. Yes. So this is the Google Form link. Kindly send your feedback, and its purpose is I will share the PDF content of the lecture also. And whatever link I am going to give the content, that link it contains all the webinars so far we had organized. So not only PDF and the videos also there. So I will send the webinars content link so for your email ID. So I hope all of you copied the Google Form link. Now you can send your questions through chat. Sir, Professor, you can observe the chat questions.
Yeah, I can see that links that are already put in chat box.
Okay. So you can stop the share and you can use the chat box, sir.
Okay, yeah, it's fine.
And you can use your video now.
Okay.
Use your video, sir.
Yeah.
So now have you popped out the chat box, sir?
Yes.
Okay. Now you can able to.
Yeah, somebody is asking. Okay, somebody is asking, how do you check the accuracy of predicted watershed? One possibility is that, once predicted watershed. Okay, I think you're talking about watershed delineation. Yeah, what we can do is, when we identify watershed boundary, one possibility which we refer to as ground truth collection, we can go to the basin and at a few locations at least, we can try to identify whether that point is locally highest elevated or not. Because watershed boundary should be drawn through a locally highest elevated points or ridge line. So if the point boundary that we have identified is not tallying with one of the points or multiple points that we identified as or potential high elevation points, that means our delineation is not correct. Therefore, we may have to apply some correction there. Otherwise, it should be correct. Okay. And if you are talking about same thing, like let's say land use categorization. Let's say you have identified some location as agricultural area. One pixel is saying it's showing that it's agricultural area. And if you have gone to that location by any chance, and if you have collected that information at that ground, if it is not agricultural area, let's say it's a barren area, then your classification is not correct. So we try to apply accuracy assessment based on that. And we also try to provide information regarding how accurate is our LULC classification. We try to quantify that using kappa statistic or confusion matrix. Many other tools are there to estimate the accuracy. I see that many number of questions are popping up. Can we use the remote sensing tool for managing the water quality and water pollution, and how? Yeah, one possible aspect is that if the water quality, change in water quality is visible through some parameter. For example, water quality is different. Let's say it's turbid at some location, it's pure at some location. The response or the reflectance that we get from those two different locations will be different. Therefore, we'll be able to identify it. In the same way, in some portion of the water body, we have, let us say, phytoplankton or vegetation, floating vegetation. And that can be identified when compared to the place where we have pure water. And that's again because we'll have more reflectance from healthy vegetation or vegetation portion of the water body when compared to the place where we have pure water. And in the same way, deep water versus shallow water, all those things can be derived or obtained through remote sensing. Multiple spectral sensing will help us to identify water quality parameters to some extent. But it is not like, you cannot really estimate dissolved oxygen from that. But the visible parameters could be identified as turbidity, phytoplankton, and any other feature which will have a different reflectance property when compared to the water body can be identified through remote sensing. Scope of research. I'm sorry, what I'm doing is, what are the questions that is visible to me right now on the screen? I'm trying to do it. I'm not going in order. Scope of research, such high costly resources are available to scholars, sir. Yes, actually, one of the important aspect is that a lot of this satellite data is now freely available. Especially if you try to go for Earth Engine machine, where it's a freely available website. From there, for a given location, you simply specify latitude, longitude, or specify the region name. For example, Andhra Pradesh or Guntur district. Then you can download the satellite image of that district or that region freely from this website, and that provides data from multiple satellites, and it collates the data and tries to make it available for any region of our interest. For example, you can download data for Delhi 2020 for Guntur district, and you can also download data for 2020 for Guntur district, and so on. So like that, for a given region, by specifying the lat lengths or the corners of that rectangular box over which you want the image to be covered, or a region name, or if you try to provide the shape file of a given region, upload it, and then you try to populate that region with a satellite image. So all such possibilities are there through this information, and this is a very popular one. I like to simply, if you type in Google free satellite images, you will get this link. That's maintained by USDA America, but we can get it. And if you want similar source, which is not freely available, but some portion of it is freely available, is NRSC Bhuvan website. There also you can freely download this data. I'm hearing someone after a long time. Okay, quick question. Spot is still at 30 meter. Oh, it's much finer spatial resolution. Spot satellite data is now available. It's a French satellite. It is now available at a much finer spatial resolution, especially if you're talking about panchromatic data from Spot. It is available at less than 5 meter spatial resolution. And that too, it is available in stereoscopic view. So we can get the DEM data, derived DEM data, for every 5 meter by 5 meter box using Spot data. Okay. And in the same way, if you try to use Cartosat data from IRS, that you may have to purchase at a very high spatial resolution, then you can get for 1 meter by 1 meter grid box the DEM data. I mean, they may not provide the data for some locations in India which are called as restricted zones like air stations, air force stations, etc. But otherwise, for most of the other locations, we can get the data by paying money for 1 meter spatial resolution without paying money with about 20 meter spatial resolution freely. So both these data sources are available even from IRS Cartosat satellite. Thank you for compliments. I'm getting compliments from many of you, but I'm looking for questions. To access water productivity, or to assess, I think. Yeah. Yeah, it's possible. Like the way I have shown you the pore points in a SWAT model, at every pore point, using the SWAT model, we can now assess what is the amount of water that is available at that location. So water quantity or water yield available with a given basin at multiple locations can be derived through this complete platform that I explained to you. All these tools, and let's say AV-SWAT, or for that matter, AV-SWAT is not the only model. You can use WIC model, you can use HEC-RAS model, many other models are available. Any of them you can try to use to get this data. Yes, you can try to estimate water quantity. Can water quantity estimation be done in a minor for a season? Yeah, it depends on the spatial resolution. So if you are trying to estimate that for a small region, like a minor, then what we need to do is we need to have the spatial data at a very high spatial resolution. For example, the one that I have used for Krishna River Basin is actually IRS-1C, that's about 22 meter spatial resolution. And here, what you can do for minor is to look at 5 meter spatial resolution that is available through Cartosat, or even 1 meter spatial resolution if we can afford to buy it. And in that case, we can assess water resources even for a minor, and that too for a season, not only for a season, even for a period which is less than a season, like a month or a fortnightly or a weekly, depending on the rainfall data available. I'm seeing lots of compliments, but let me see. Yeah, someone simply asked, dear sir, LIDAR in DEM. Yeah, LIDAR, if somebody can afford, especially this happens for urban areas or cities, we can try to get LIDAR data. And LIDAR data, if we can get it, it is available at a very high spatial resolution of less than a meter. We can talk about centimeter scale to get the digital elevation data using LIDAR. And LIDAR also provides the advantage that we can overcome the problem of surface topographic information like tree canopy, building heights, etc. And those can be avoided using LIDAR. But most of the LIDAR that we talk about is actually for urban areas, is basically using ground-based LIDAR platform. You just put it on a Jeep or a car and take the LIDAR all around to acquire the LIDAR data. And that will be at a very fine spatial resolution, which is very good for urban hydrology. It is totally of money if you try to do it for a river basin. Scope of research, such high, okay, that I already answered. Dr. Ramarao, you have to help me if I'm missing any question. Can we do contamination studies like groundwater contamination? What I have to just explain with a small remark that, as far as groundwater contribution is concerned, it is not very easy to assess directly through remote sensing. But remote sensing can be used as a tool to map the potential groundwater zones, and based on that, we can talk about contaminant transport. So if the groundwater is polluted and the contaminant in the groundwater is transported laterally, then it is not very easy to estimate it only through remote sensing. Remote sensing can only be a partial tool that could be used for that purpose. Okay. Dr. Ramarao, can you tell me if there's any question?
What will be
or
the
if any of your question asked a question
in watershed management or assessment?
Yeah. Briefly answered. LIDAR, the advantage is available at a very high spatial resolution, and that is extremely useful for urban hydrology. Nowadays, if there is a rainfall, intense rainfall in a city like Bombay or Chennai, and if you want to model a flood that is happening, then you require very high resolution DEM or very high resolution flood model like HECRAS or SWAM model or something like that. And to do that, if you have LIDAR data, we can do very good in terms of modeling those high peak events as far as urban hydrology is concerned. And it is also useful in case if the stormwater drainage structure is below the ground, underground. And then if the stormwater drainage structure is actually mapped onto GIS along with the LIDAR data, then we can model the flood flow or storm runoff through a basin or through a small portion of the city using this LIDAR data. So LIDAR data is very useful in that context, especially for urban hydrology. Cities and dwells and the places where you want to focus on putting the stormwater drainage system, and if you want to go for urbanization of a given location, you can try to see whether it is going to be flooded very frequently or not. And if you want to talk about flood insurance for a house property, again, LIDAR data is very useful to talk about using it as a DEM tool for modeling. So yeah, LIDAR data, although it is expensive, it is now become very useful in urban sector.
Sir, one question is from Hussein MD. How to
Oh,
download
Mohammed Yusuf.
shape files of Nellore district
Yeah.
and use for groundwater modeling software?
Yeah. As I said, for groundwater modeling, DEM data alone is not sufficient. DEM data tells you the surface topography, but what you require is the water table profile, and that need not match with the surface elevation profile. So this will become one tool to talk about where could be more amount of infiltration into the ground and percolation into the ground. But if you want to draw the groundwater movement, you also require the water table level at multiple locations through observation wells, etc. And that cannot be easily derived through remote sensing. But that can be floated through DEM and other ancillary data that we have, let us say, from Central Groundwater Board. We can put them together in GIS database and then do the modeling, let us say, using one of these groundwater models, which are very popular for hydrologic modeling. So there, this will become a partial tool. Any other questions, Dr. Rao, that I missed?
And one question from Sailaja, resolution of SRTM data that is available now.
Yeah, I mentioned this. This is about 80 meters. So for every 80 meter by 80 meter grid box for the entire country, we have the elevation data available from SRTM. But if you are looking for much finer spatial resolution, freely available, you can look for ASTER data, ASTER DEM data that is available at 30 meter spatial resolution, which can also be freely downloaded. And it is also available from Cartosat DEM. But if you can pay and get it, then Cartosat DEM at 1 meter spatial resolution or at least 5 meter spatial resolution is available.
There is another question from Ratnakumar Vakalgadda. In the case of a dam break analysis and thereby inundation map preparation for a disaster management map, 20 meter spatial resolution DEM data is too coarse to use. Then in those cases, what has to be done and how to get reliable cross-section data for dam break studies?
Yeah. Generally what happens is, for the reaches where the dam and its downstream are there, generally we get the elevation data at much finer spatial resolution if it is available from any source, including the source that I mentioned to you, like Cartosat, ASTER, or even finer spatial resolution data. And if you can afford LIDAR data, then that DEM data will be very useful. And as a matter of fact, we can try to trace for a given flood magnitude or flow magnitude from a dam break, okay, a dam breach, then how the dynamic wave should be routed through the floodplain can be done through a very good DEM source. And we have been doing it for a good number of cases, especially through to Central Water Commission, through one major project called DRIP, Dam Rehabilitation Project. So there we are trying to see what happens in an unforeseen event of a dam breaking, how the area get inundated, and every location or every pixel, let's say 2 meters by 2 meter pixel, if it is inundated, if we also have the land use land cover map for that pixel, then we know what is going to be inundated. Is it agricultural area, or is it an urban housing area, or is it simply barren area? So all such information can be extracted pixel by pixel, and that's being done. That can be done using this DEM and remote sensing together with a reasonably good hydrologic model. It's doable. Some works are done for some riverways, some dams.
There is another question from Srinivasulu Gopu.
Oh yeah.
Which satellite data is useful for modeling seepage flows in canals or rivers?
That's not very easy. If it is an unlined canal, then for unlined canal, we can try to estimate seepage through some kind of model like WIC or something, but it will not be very accurate because the seepage through canal system will be such a local phenomena that you require at very high spatial resolution the data itself, first of all, and then we can try to model it. But we have to have some information of geography below the surface, because the properties of seepage will depend on the soil below the ground. And if we have that information derived based on the soil type and others, then we can still use, but I tell you, there remote sensing and GIS can play only a supportive role, but we have to use other tools to estimate the seepage from the canals.
There is another question from YN Srivatswa. Structural failure of irrigation structures can also be detected. For example, some canal line failure.
Yes. Again, I will refer to this again with two unlined canals first of all. Unlined canal means both sides you'll have a bank, and that, it may be earth structure or earthen bank, and that bank in a places where it is prone to failure or likely to fail. Okay, the soil profile here, as well as the other ancillary information, if possible, even an indication of cracks, etc. But we can also talk about river breach locations, potential river breach locations can be identified through remote sensing. But I thought I'll run time with that. We did analysis for Kosi River breach using remote sensing of GIS.
Sir, for further questions, they will send mail to you, sir.
Okay.
Okay,
Yeah.
sir. So thank you, sir. So,
okay.
Thank you, one and all. So, sir, once again, we will meet tomorrow, 6 p.m. So thank you, one and all.
Thank you all for participation. Bye.